Swayam Prabha. Digital India. Educated India.
This is the last lecture in this course. So what we will do is we will quickly recall what we did in this course and briefly discuss a couple of directions in which we can move forward. So when we started this course, these were the topics which were proposed to be covered. The approximate methods and finite element method, dynamics of truss and planar frames, damping models and analysis of equilibrium equations, dynamics of grids and 3D frames, and some computational aspects like solution of equilibrium equations, eigenvalue problems, model reduction and substructuring. Then review of dynamic stiffness matrix and transfer matrix methods. Then dynamics of plane stress, plane strain, plate bending, shell and 3D elements. Then applications to earthquake engineering and vehicle structure interactions. Then application of finite element analysis for elastic stability problems. Some issues about treatment of nonlinearity and questions on finite element model updating and how a finite element method is used in hybrid simulations. So excepting the last topic, we have broadly covered all these issues. So the course has been divided into basically 11 modules. In the first module we started with approximate methods and finite element method. Then this was followed by analysis of planar trusses and frames. Then we spent time on integration of equations of motion, then analysis of grids and three-dimensional frames, then time integration of equation of motion. In the third module we considered normal mode representations. Here we looked at time integration. Then questions on model reduction and substructuring were addressed in module 6. Then analysis of 2 and 3 dimensional continua. We spent some time discussing plane stress elements, plate bending elements and facet shell elements. So that covered the module 7 and 8, and in module 9 we covered quite a bit of ground on structural stability analysis. Then we briefly considered two topics, that is finite element model updating and how to deal with nonlinearity in finite element models. So I would like to acknowledge at this stage authors of these books whose work I found quite useful in preparing these lectures. So at many places I have my lectures were fashioned after some of the coverage in some of these textbooks. So we began by considering application of Hamilton's principle to simple systems like mass spring dashpot system, and we derived the equation of motion by applying Hamilton's principle, and then generalized this to continuous systems. So this is actually vibrating rod, and we saw that application of Hamilton's principle enables us to derive the equilibrium equation and also a set of valid boundary conditions. Now the boundary conditions themselves were classified as geometric, forced or kinematic conditions and then natural boundary conditions. We covered several examples where there was combination of continuum elements and discrete elements, used Hamilton's principle and derived the equations. We then moved on to theory of Euler-Bernoulli beams. Again, by using the Hamilton's principle we derived the gowning equation and the relevant boundary conditions, and we saw that the field equation will be of this form in free vibration, and there are 16 combinations of single span beams which emanate from the application of Hamilton's principle. So these are various boundary conditions which are appropriate for Euler-Bernoulli beam cases. Now in the analysis of free vibration characteristics, we began by discussing about Raleigh's quotient. So we formulated the Raleigh's quotient for discrete multi-degree freedom system and few continuous systems, and an important property of Raleigh's quotient was that it was bounded between square of first natural frequency and square of the nth natural frequency in a n degree freedom system. Whereas for continuous system there was only a bound on the lower value r was greater than omega 1 square. Now Rayleigh's quotient you can derive without writing the equation of motion. So that is a quick way of finding natural frequencies, and phi of x are the trial functions, and the choice of these trial functions plays important role in application of these methods. And among different choices of trial functions, the one which provides the lowest value of Rayleigh's quotient provides the best estimate to the first natural frequency. So in our endeavor to lower the value of Rayleigh's quotient, we introduced the Rayleigh-Ritz method, where the trial function was represented in a series of orthogonal functions typically, and ANs were the generalized coordinates, and we minimize Rayleigh's quotient with respect to these ANs. So these phi n of x are a set of known linearly independent functions which satisfy all the boundary conditions to start with. Then we found out ANs which minimize this Rayleigh's quotient, and that helped us to find not only the first natural frequency but also approximations to higher natural frequencies. Then starting from field equations, we developed the so called method of weighted residuals. So for example, for the beam equation, this was the field equation, and we started by approximating the solution over 0 to L in terms of n generalized coordinates a n of t to be determined and a set of known trial functions phi n of x. So these phi n of x are valid over the entire domain of the beam. So when we substitute this into the field equation, we get an error that we call as residue, and the method of weighted residual essentially minimizes this residue in some sense. So that leads to a set of discrete equations, that is the space variable x has been now discretized and we are left with time which is still continuous. So this is a semi discretized equation of motion for the system, and this leads to the concept of mass, damping and stiffness matrix and a forcing vector. So what method of weighted residual achieves is that a partial differential equation governing the behavior of a continuous system has been replaced by an equivalent set of ordinary differential equations which are initial value problems with a view to obtain approximate solutions. The notion of this method of weighted residuals was not unique, and there were several possibilities, and we talked about least square method, collocation method, Galerkin method, subdomain collocation, Petrov-Galerkin and so on and so forth. The basic idea here is the weighting function changes for these different methods, and we also applied this to a few problems and saw how it works. So basically there was a residue and a weight function, and by selecting n weight functions and equating this to 0, we got n number of equations, and this is the resulting equation. This is broadly the class of methods known as method of weighted residues. We also considered certain other additional methods, and we introduced the strong form, weighted residual form and weak form of governing equations while discussing this. Now the problem with method of weighted residuals as discussed here is that these trial functions were globally valid. So if we have a very more complicated domain, to construct phi n of x which are globally valid will be difficult, and also the generalized coordinates a n of t that arises here do not have a direct physical meaning. Now this led to the discussion on finite element method. What we did was the domain of interest was partitioned as shown here, and the field variable at these points known as nodes were taken as generalized coordinates, and these subdomains which are known as elements, the field variable within an element was interpolated in terms of these nodal values using polynomials. So each of these elements have, for example, have simple 4 unknowns and a interpolation function. So there is nothing really superlative about the performance of a single element, but the entire finite element procedure is such that when all this is assembled, it delivers a very superlative performance in terms of analysis of very complex problems involving complexity in geometry, constitutive laws and so on and so forth. Now the word finite element, the phrase finite element method, we try to explain the word finite here originates because the field variable is approximated in terms of the value of the field variables at a set of nodes, finite number of nodes, that is where the word finite arises. The element of course is that we are the domain of interest is approximated by omega tilde, and this is taken as union of a set of non-intersecting subdomains, and each one is an element, and within an element the field variable is approximated in terms of interpolation function and nodal values. So, this renders credence to the name element. The method is of course it indicates that finite element method is an approximate numerical method to obtain solutions to partial differential equations or variational problems. So, these omega I are elements, xi tilde are nodes, and capital N is a number of nodes in the approximated model. Now, using that what we did was, for each of these elements we derived the equation of motion that led to the notion of element level mass, damping and stiffness matrix and a forcing vector, and this is formulated in the local coordinate system. Then the element level equation of motion is transformed to global coordinate systems. We developed how displacement, velocity and acceleration and force vectors are all vectors, and they obey certain rules of transformation, and based on that we can construct the transformation needed to form the mass, stiffness and damping matrices in the global coordinate system. Then to construct the structure matrix for the entire structure, these matrices need to be assembled. So, basically energies in different subdomains add, and that forms the basis of forming the global equation of motion, and at this stage we have not yet partitioned the equation into unknown displacements and unknown reactions, and we have not yet imposed the boundary conditions. So, upon imposing the boundary conditions and partitioning the vector u accordingly, we got the final equation of motion for the system for the unknown displacements as mu double dot plus u dot plus ku equal to f of t, where u of 0 is u naught and u dot 0 is u naught dot, which are initial displacement and velocities. We considered various complicating issues. We started by studying planar frames and modeled elements as Euler-Bernoulli beams. We considered questions about how to deal with a hinge and a roller on an inclined support, etc. That is, how to set up suitable constraint equations in terms of degrees of freedom to correctly capture the presence of a hinge or an inclined roller, and so on and so forth. One important observation we made was that while the displacement field across the element is continuous, but when it comes to evaluation of stresses, for example in the case of an axially vibrating bar, there will be discontinuities. So, the finite element method thus introduces discontinuities across element boundaries in certain quantities which are not there is no discontinuity in an exact solution. So, this is one of the limitations of finite element method. Next, we started looking at some issues about dynamics. So, we derived the input output relation in time and frequency domains. We introduced the notion of an impulse response function and complex frequency response function. These quantities become matrices for multi-degree freedom systems, and these are the definitions for the impulse response function and the complex frequency response function. Now, in formulating the in trying to solve the governing equations of motion, we started by looking for certain coordinates in which the degrees of freedom become uncoupled, and we found that there are transformations from a given coordinate system to certain natural coordinate systems in which the degrees of freedom become uncoupled. The consequence of that is a coupled set of ordinary differential equations are solved as a set of uncoupled either second order differential equation or first order differential equation, depending on how we represent the equation of motion. So, we started another element in our solution strategy, modeling strategy, was introduction of damping. For linear systems, the damping models were either viscous or structural and so called classical or non-classical. So, the classical damping models are those in which the undamped normal modes uncouple the equation of motion, whereas that is not true for non-classical damping. So, we addressed question of how to uncouple equation of motion for each one of these 4 damping models. And we introduce in doing so several quantities like receptance, mobility, accelerance, dynamic stiffness, mechanical impedance, apparent mass, and so on and so forth. So, the FRF calculations, that is the representation of system response in frequency domain, we developed several methods. For example, in viscously damped system, one could directly invert the dynamic stiffness matrix and get that, and similar strategy can also be adopted for structurally damped systems. But each one of these calculation can be carried out in terms of mode superposition method by using mode superposition method, and that requires the determination of the appropriate natural frequencies and mode shapes. So, this we did for all the 4 cases of damping, that is structural, viscous, proportional and non-proportional damping models. In certain class of problems in linear structural dynamics, where if attention is focused only on steady state behavior under harmonic loads or loads which permit Fourier representation, one can use what method known as dynamic stiffness matrix. Here we assume that in a beam, for example shown here, this is an Euler-Bernoulli beam, if the nodal displacement and forces are all harmonic at the same frequency as shown here, what conditions these amplitudes delta k and pk should satisfy so that the governing equation is satisfied. So, that leads us to the definition of the dynamic stiffness matrix that we derived for Euler-Bernoulli beam, and we also considered alternative representation in terms of transfer matrices briefly, and to do that we introduced, for example, in axially vibrating rod a state vector comprising of displacement and axial force, and how it is related from at this node the amplitude and displacement of force and displacement, how they are related to amplitude of force and displacement at the other node. So, this is so called transfer matrix. So, this can also be derived for axially vibrating bar as well as beam and other more general problems. Then we moved on to analysis of certain built up structures, a planar frame like this, or a grid structure like this, or in more general situations a 3-dimensional frame. So, to analyze a grid element which is displayed here, bending in these beams cause torsion in the other beams. So, we need to include effect of twisting, and that we spent some time and developed the stiffness matrix associated with torsional degrees of freedom, and we developed the relevant structural matrices that included the flexure and twisting. This we generalized to 3-dimensional beam element, and here we considered U beam element typically has 2 nodes and 6 degrees of freedom per node. The degrees of freedom are translation in x direction, that is axial deformation, and rotations about z axis and about y axis at the 2 nodes. So, and of course translations here. So, this we developed, and the way we approached the problem was we assumed that cross sections have symmetric properties, and we set up the expression for axial deformation, twisting, bending about z and bending about y, where for twisting we use the theory of torsion of prismatic members, which we developed in some detail as we went along. The kinetic energy itself comprised of axial deformation, twisting, bending about z and bending about y. In later discussions we also introduced strain energy due to shear deformation and kinetic energy due to rotary inertia, that led to the treatment of deep beams. Now, for all these class of systems, that is fairly broad class of systems, the final equation of motion always had this form. For the purpose of discussing numerical methods for solving these equations, we introduced the nonlinear terms with an anticipation that this we will be dealing with later in the course. So, we developed several methods for numerical integration of these equations. These equations at this stage are semi discretized, that means time is still continuous, the spatial variables have been discretized. So, the basic idea was to replace the time variation in time again by discretizing time. So, we considered solution of this equation at a set of discrete time instant t0, t1, t2, tn, with some step size delta Tn, Tn plus 1 minus Tn. The basic idea was to replace the derivatives appearing in these equations by suitable finite difference approximations and convert these equations into appropriate algebraic equations and treat their solution using algebraic methods. So, we discussed several methods, forward Euler, backward Euler, central difference and Newmark's family of methods, and the so called HST alpha method and the generalization, and HST alpha with operator splitting. We discussed questions about explicitness of these algorithms and what is implicit and explicit algorithms, so on and so forth. We also discussed for linear time invariant systems the question of spectral radius and how it influences choice of step size, and that would mean how to select step size so that the solutions would be stable. In discussing this, we identified certain desirable features for numerical integration schemes that we need to use in dealing with large scale problems. The algorithm should have at least second order accuracy. They should be unconditionally stable when applied to linear time invariant systems. Then there should be controllable algorithmic damping in higher modes, which would require us to investigate the spectral radius as frequency becomes large and frequency becomes small. There should be no overshoot, that is excessive oscillations during first few steps should not be there, and the solution should be self starting and no more than one set of implicit equations to be solved at each step. So, we illustrated some of these requirements with specific methods. Next we considered questions, two questions on dealing with large scale problems. The first question was on model reduction. That means suppose if I have a large scale finite element model such as this, how can we reduce it to a model with lesser degrees of freedom? This arises, originally this type of questions were asked in the context of when computational resources were limited, but presently those questions are probably not that relevant. But what is still relevant is when we deal with situations where we are comparing the performance of a computational model with an experimental model and we are trying to reconcile the two models, then we need to reduce the for example, typically the size of computational model to match the degree of freedoms that are measured in an experimental work. So, the experimental degrees of freedom typically tend to be small than the computational model. So, either we can reduce the size of the computational model or expand the size of an experimental model. So, that requires certain computational procedures, and we discussed three methods: static condensation, dynamic condensation and system equivalent reduction and expansion process. We saw that this SEIREP method is the most versatile. It preserves a set of normal modes in the reduced model, whereas in a static condensation there is no such promise, not even one mode need to be correctly captured, whereas in dynamic condensation it is possible to capture at least one mode correctly. Next we considered situation where again a structure made up of different components, and the question was, suppose these different components, for example as in a satellite structure, if are being designed and developed by different teams, how do we produce a finite element model for the combined system? So, here we discussed two class of methods, that is spatial coupling method and modal coupling method. That in discussing the modal coupling method, we discussed the component mode synthesis, which is one of the well known coupling techniques that is used in practice. After the foray into certain computational aspect, we returned to the question of element development, and we moved on to two dimensional elements. We considered the membrane action due to in-plane loads and bending action due to transverse load. So, we began by discussing membrane action. We developed linear triangular plane stress element and we generalized it to linear quadrilateral element, and that led to the notion of isoparametric formulation, which basically was necessitated by new requirement to integrate these integrals that appear in the formulation of element stiffness and mass matrices. So, the idea is the geometry of the structure is mapped to a master element like this, and we interpolate the coordinates in this x and y in terms of psi and eta using the same trial functions as is used to represent the field variables, displacement field variables. So, This transformation was essentially made to facilitate evaluation of the integral leading to the determination of stiffness, mass and forcing stiffness and mass matrices and the forcing vectors. We moved on to the discussion of solid elements. We considered tetrahedron element, rectangular hexahedron element, pentahedron, isoparametric hexahedron elements, and we developed some of these formulations and we discussed, I think, 8 noded element with 3 degrees of freedom per node in isoparametric formulation, how this can be done. Next we considered problems where there was axisymmetry in the geometry, that means geometry was 3D axisymmetric solid, it is not, the object is not necessarily prismatic and it is not necessarily thin or thick as in the case of plane stress plane strain models. There were certain restrictions that were placed on surface tractions and body forces, and that under certain assumptions on these variations, this type of problems can also be reduced to 2-dimensional problems, and we formulated one such element. Next we considered plate bending problems, and we developed several plate bending elements. We saw the question of how certain element formulations lead to non-conforming non-conformity, and how to overcome that. We discussed several of those strategies. Then we also discussed how to deal with plates that are stiffened by beam elements. So we developed elements for dealing with this type of situations. So at the end of these lectures, we were ready with stiffness and mass matrices and damping matrices and forcing vector for a wide class of problems, and next we moved on to questions about stability analysis. The question of stability was addressed with respect to either a steady state of rest or periodic motion or random motion. We can address in this form. We considered state of rest and periodic motion, we did not consider random motion in these lectures. So the question we asked was, what is the influence of an externally imposed disturbance on these states of rest and periodic motion? If as a consequence of this disturbance, if the response dies, the disturbance dies off, then we say that the state is stable. Then if the original state is not restored, the two possibilities is motion grows without limit and the state is unstable, or if motion neither grows nor decays, then we reach a stage where we will not be able to resolve using the first order approximation whether the state is stable or unstable. This type of questions we began by addressing in context of beam columns, and for beams carrying axial loads, we notice that there is a dramatic change in the nature of the solution. For example, if we consider this problem where there is a single span beam carrying a transverse load q of x and axial load p, while writing the expression for bending moment at this cross section, we were able to write the bending moment due to q of x, but when it came to a question of writing the expression for bending moment due to p, we used the deformed configuration of the beam. So this was our first taste of issue of nonlinearities, where to find bending moment m of x we use undeformed geometry, whereas to find the contribution from axial loads we use a deformed geometry. So that played a crucial role, and we saw that the presence of an axial load plays a crucial produces dramatic effect, and some basic notions like principle of superposition become the first casualty in treatment of axial loads. So we recalled some results on beam columns, and for example this single span beam carrying a load q and axial load p, we derived the expression for mid-span displacement and rotations at the supports and maximum bending moment when load was applied symmetrically, and we showed that these responses typically had a structure where delta naught, theta naught and m naught were responses with p equal to 0. When the axial loads were absent, whatever was the response, they got magnified or modified by certain functions known as stability functions. So we introduced chi of u, epsilon u, xi of u, and this graph shows typical plots of these stability functions, and the most interesting aspect of these functions is that at certain values of load parameter, axial load parameter, these modifications become unbounded, thereby indicating that at these values of axial loads the structure would not be stable. So, we considered we interpreted presence of a transverse load or our inability to apply axial loads in a truly perfect manner or presence of an initial imperfection as manifestations of certain imperfections in the system. That means, these three problems we showed that they are all mathematically equivalent, and we interpreted them as manifestations or departures from an ideal situation. Now, how about the study of an ideal situation itself? That led to the notion of an eigenvalue problem to determine the value of axial load P at which the neighboring equilibrium position becomes possible. So, this led to the notion of Eulerian buckling loads, and we developed that theory. Then we briefly considered question of stability of dynamical systems, because we also asked the question on equilibrium of systems in motion. So, we considered differential equations of this form, and we defined the notion of equilibrium points where x dot and y dot are 0, and we investigated the influence of small perturbations on these equilibrium positions, and we found that the nature of the equilibrium points, also known as fixed point, depend on eigenvalues of this gradient matrix when it is evaluated around these fixed points. Next, we enunciated two axioms for analyzing stability of more general class of problems, and these axioms led to the energy methods for stability analysis. The first axiom stated that a stationary value of the total potential energy with respect to generalized coordinates is necessary and sufficient condition for the equilibrium of the system. So, the first axiom provided the condition for equilibrium. The second axiom helped us to establish whether that equilibrium position is stable or not. A complete relative minimum of the total potential energy with respect to generalized coordinates is necessary and sufficient for the stability of an equilibrium state of the system. Now, based on this, we analyzed several problems. We considered specifically two problems. One is buckling of an Euler-Bernoulli beam, and we derived this load deflection diagram of P versus this transverse displacement delta, and we traced the load deflection paths lose their stability at certain points and they bifurcate. That is one aspect of it. In structures such as this, which are shell structures, can be thought of as something being similar to this type of structure. Suppose there are two rigid links supported as shown here, and there is a load P, and we start loading this structure that is at theta equal to 0, P equal to 0, we have initially some displacement, and as we go on increasing this, the loading path the load and the displacement increase simultaneously, and they reach a critical value here at which the structure loses stability and moves to a far away equilibrium position. So, this type of behavior is known as limit load buckling. That means, when the structure loses stability, the equilibrium position is far away from the position at which it lost its stability. Whereas here, when P approaches P critical, a neighboring equilibrium position becomes possible. Now, to formulate the problems of stability using finite element method, we developed what is known as geometric stiffness matrix for different elements, and a general theory for that required us to introduce the nonlinear relationship between displacements and strains. So, a pre-stress that exists does work on the subsequent deformations, and that helps us to formulate the geometric stiffness matrix, and we showed that the an eigenvalue analysis of the elastic stiffness matrix and the geometric stiffness matrix, that means Kx equal to K sigma lambda K sigma x helped us to determine the loads at which the structure would lose stability. Now, another important question we addressed was the interaction between nonlinearity and imperfections. So, to illustrate that, we considered three archetypal problems. Here in these three problems, AB is a rigid bar which is identical in all these three cases, but supported in three different ways. Here it is supported through a spring here it is supported through a spring here, whereas here it is supported through an inclined spring. Conceptually, we did a thought experiment in which we designed these values of we selected K1, K2, K3 so that all these 3 systems had the same value of critical load. But we plotted the load deflection diagram for each one of this, and for this case we found that the load deflection path rises along a stable path and it continues to evolve along a stable path without encountering a unstable path. Now we also introduced in each of these cases slight imperfections and investigated the influence of these imperfections. In the second case, with a system with a slight imperfection, the load load deflection path rises on a stable path and it encounters an unstable path and the structure loses stability. So here the influence of imperfection is to lower the load carrying capacity of the structure, and this in the final case similar behavior is observed, and again a stable path culminates in a unstable it encounters an unstable trajectory. So in an experimental work what happens is, although these 3 systems are designed to have the same critical value, it is observed that this is the critical load evaluated for the third system will be less than what is evaluated for the second system, and this will be less than what is evaluated for this system. So these 2 systems are known as imperfection sensitive structures, where the critical load carrying capacity depends on imperfection, and plates and shells display this type of behavior. We considered subsequently another class of problems where the axial loads were time varying. We considered 2 situations where there is a tall stack under biaxial earthquake ground motion and also a bridge structure which is traversed by a vehicle. So we formulated equation for these 2 systems and showed that the coefficients in the governing partial differential equations are time dependent. So such systems are known as parametrically excited systems. We also considered another class of problems wherein the loads were not time dependent, but the direction of the load in the one case, for example, if the load P its direction does not change during process of deformation, a static analysis would tell us how this structure behaves. But if the load were to be such that it remains tangential to the deformed axis, a static analysis reveals that this structure is always stable, but a dynamic analysis shows that there is a finite value for P beyond which the structure becomes unstable, which is consistent with what we anticipate. So these 2 cases, parametrically excited system and the so called follower force models, indicated situations under which a dynamic analysis needs to be done to infer stability of the system. Now in this context we considered 3 problems. First one was how to characterize resonances in systems governed by equations of this form, where the mass, damping and stiffness matrices are time dependent, and especially when these time variations are periodic. Next, how to arrive at finite element models for partial differential equations with time varying coefficients. Subsequently, we also consider the question if there are any situations in statically loaded systems wherein one needs to use dynamic analysis to infer stability conditions. So while answering the first question, we developed the theory of flow case coefficients, and we developed a procedure on how to evaluate the flow case matrix, and we showed that the eigenvalues of the flow case matrix enable us to answer these questions. So to answer the second type of deal with second type of problems, we considered a beam carrying a moving single degree freedom system, and we formulated the governing equation and developed a finite element model based on weak formulation, and showed that the element mass matrix, damping matrix and stiffness matrices are unsymmetric and time dependent for this class of problems. The interaction between the vehicle and the structure induces these unusual features. So these type of problems need to be handled only in time. They do not have natural coordinates, the concept of natural frequency mode shapes are no longer valid. We briefly then considered questions on the role of finite element modeling in dealing with existing structures. So before a structure comes into existence, we have only mathematical models to deal with that type of problems. That is typically what we do when we design a structure which is yet to come into existence. Moment the structure comes into existence, of course the mathematical modeling techniques still remain valid, but also additionally we have experimental tools becoming available to us, and thus we can measure the performance of the structure under either diagnostic loads or operational loads. So, the prediction in these situations from an experimental model and a mathematical model often do not agree, and the question is how do we update the mathematical model to reconcile these two predictions. So, this leads to the topic of finite element model updating, and we briefly reviewed the issues related to this question and developed specifically one approach that was based on so called inverse sensitivity analysis. So, we derived the updating equations in terms of changes to be made to system parameters based on observed changes in certain system responses, and these we showed is connected through a matrix known as sensitivity matrix. So, we considered several issues here, how to formulate this S matrix and how to the resulting equations will be often a set of over determined equations that require special techniques to solve them. We discussed pseudo inverse method, singular value decomposition and Tikhonov regularization approaches for dealing with this class of problems. In the final part of our course, we started talking about how to deal with nonlinearity. So, the sources of nonlinearity we identified were either related to nonlinear strain displacement relations, in which case we said the nonlinearity is geometric nonlinearity, or the relationship between stress and strain could be nonlinear. Then we call this a nonlinear constitutive, here we had nonlinear constitutive laws, and this type of nonlinearity was called material nonlinearity. Then nonlinearity associated with boundary conditions as in contact problems or free plays and so on and so forth induces a different kind of nonlinearity. The energy dissipation mechanisms also bring in newer forms of nonlinearity. It could be friction, it could be impacting at free plays, etc. Now, while formulating this, we can conceptualize different frameworks. For example, the displacement and rotation of a structure could be small, but the stress strain relationship could be nonlinear. So, this is small deformation, but materially nonlinear, geometrically linear, materially nonlinear. Here the material could be linear or nonlinear, but there are large rotations and small strains. So, one of the questions that needs to be carefully addressed in dealing with nonlinear problems is treatment of rotations. So, in a more general class of problems, of course, material could be linear or nonlinear, there are large rotations and large strains. These are the most general class of problems which are most difficult to deal with. A simple illustration of a nonlinear problem with nonlinear boundary condition is shown here. Suppose this support there is a free play this gap, and as the structure deforms, if this gap is negotiated, then this spring stiffness will come into action, and the stress strain typical stress strain plot will have this kind of feature. Here the loading and unloading path will trace each other. This is a geometric nonlinearity, whereas if you are dealing with material nonlinearity, the loading and unloading paths will be different. Upon removal of the load, there will be a permanent set. So, in dynamical systems, we saw that the Gauni equation will be of the form mx double dot plus cx dot plus kx, and a nonlinear function of instantaneous values of displacement and velocity, and this is the geometric nonlinearity or elastically nonlinear system behavior, whereas this one, the second term, the force of resistance depends on entire time history of the response up to the current time instant. So, this is hereditary or memory dependent nonlinearity typically arising due to material nonlinearity. So, this is a more general class of problems. In formulating the finite element formulations for nonlinear problems, we found that we needed to introduce certain newer measures for strains and stresses. For example, if you use infinitesimal strains for a body under rigid body rotations, the strains would not be 0, whereas we know that under rigid body rotations the strain should be 0. So, newer measures of strains are needed which satisfy two requirements, namely that rigid body motions imply 0 strains, and for small strains the infinitesimal strains definitions are restored. Now, similar issues about stresses definition of stress measure also were considered. The Cauchy stress tensor, which deals with deformed configuration, the force field and area in a deformed configuration, was difficult to use in an analysis simply because we would not know the deformed geometry when we develop the solution. So, we developed two alternative definitions for stresses, that is Piola-Kirchhoff, first Piola-Kirchhoff and second Piola-Kirchhoff stress tensors. So, to develop the different measures of stress, we interpreted stress as a measure which conjugates with a measure of strain to produce a internal energy, or as a quantity which produces a traction vector in conjunction with a normal vector defined with respect to a surface element. The principle of virtual displacements was used to formulate the problems, and the problem was, if you use Cauchy stress tensor and Eulerian strain tensor, which are defined both are defined with respect to deformed geometry, we can set up the expression for the virtual work, but the problem is, as I already said, the deformed geometry would not be known. So, the volume over which we need to evaluate these integrals would not be known in advance. So, what we do is therefore introduce suitable strain and stress measures that helps us to evaluate these integrals over known configurations. So, that is how we developed nonlinear problems. In nonlinear problems, we recognize that if a structure is carrying a particular load P, we cannot apply the entire load in one stroke. So, we divide the load 0 to P into small increments, and we trace the solution as the load is incremented by small amounts. During an increment of a load, we can linearize certain system behavior, and that helped us to formulate the complete finite element procedure to deal with these problems. So, kinematically we considered three types of approaches: the so called total Lagrangian approach, in which the base and reference configurations coincide, and this problem is solved with respect to the configuration in the reference with respect to the reference configuration. Whereas in updated Lagrangian approach, the reference configuration was updated as the loads were incremented, and the increment between the reference configuration and current configurations were taken to be small, but the reference configuration itself was updated at every step. This we did not discuss, although I briefly mentioned co-rotational formulation, where we first form the co-rotated configuration, that is the base configuration undergoes rigid body motions. This is exaggerated, this will not be so large, need not be so large, actually CGs would coincide here. The base configuration is used as a reference to measure rotations, whereas co-rotated configuration is used as a reference to measure current stress of stress and strains. Now, we developed the total Lagrangian approach and updated Lagrangian approach, based on which we formulated the the virtual work. These are the virtual work principles, and we formulated the structural matrices. So, this is a kind of a gist of what we tried to achieve during the course, and towards the end of the last lecture I briefly mentioned topics that could be followed up as a based on material covered in this course. What was not covered in any we did not pay any attention was questions about material nonlinearity. So, we should study you should study the subject of plasticity and pay more attention to formulation of constitutive laws to be able to do this. Similarly, in the questions about stability analysis, we again did not consider material nonlinearity. Now, there are other topics about which I have briefly talked about. One is hybrid testing, among others Bayesian filtering, etc. I would like to spend few minutes explaining what is hybrid testing and what are the issues about uncertainty modeling and finite element method. Now, what is the role that finite element models play in structural testing? Now, there are different testing strategies available in vibration engineering. One is what is known as pseudodynamic test, that typically helps us to handle questions about complicated inelastic behavior under dynamic loads using basically static methods of experimental investigations. Then there is another one known as real time substructure testing. It deals with treatment of interacting primary and secondary systems in an vibrating environment. So, these techniques are being developed in the field of earthquake engineering. So, traditionally in earthquake engineering we have either a shake table on which we mount the structure to be tested, and or we have a reaction wall based system where there are servo hydraulic actuators which apply dynamic loads on models like this. The shake table testing, the load time history, that is earthquake load time history is applied in real time. The length of duration of the applied acceleration is equal to the length of the observed earthquake signal. The problem with this approach is limitations on payload capacity of shake tables. The best shake table that is currently available you may not be able to test say a building which is taller than say a 5-story building, or study interaction between soil and structure or fluid and structure and issues like that. So, there is a need to geometrically scale the test structures to be able to use shake tables. On the other hand, in effective force testing this limitation is overcome to some extent, but still the dimensions of the structure to be tested is governed by the dimension of the reaction wall system. Now, in hybrid simulations what we do is we divide the test structure into an experimental part and a numerical part, and we try to avoid scaling either of time or of geometry to the extent that is possible. So, in a typical pseudo dynamic testing, suppose this is the test structure and these arrows represents actuators, and this is schematically the actual hardware is shown here. This is servo hydraulic actuator which is under computer control. Now, we start by modeling this system as mx double dot plus cx dot plus r of x is equal to the applied ground motion. We treat that r of x which captures the inelastic behavior of the system as unknown. On the other hand, we assume that the inertial properties and damping properties of the system can be modeled computationally. So, part of the structure, namely inertia and damping properties, are modeled computationally, and part of the structural model which captures stiffness properties is measured experimentally. The way the experiment proceeds is we start integrating this equation with possibly in a linearized model for the stiffness, and integrate from say 0 to delta t. That tells us how the building has displaced. X of t is a vector of different nodal displacements, and we apply those displacements on the structure. These actuators are under displacement control, and as a consequence of applying those displacements, there will be reactions that are set up in the actuators which we measure using load cell, and that helps us to determine the stiffness. That value of stiffness is put into the equation of motion, and the load is incremented from delta t to 2 delta t, and at every time the actuator displacement is determined by solving this equation, and the stiffness is determined by actual measurement. Now, these displacements were applied statically. So, that is why this is called pseudo dynamic testing. So, in this approach the time is slowed down. A 30-second earthquake event can be expanded for 2 hours or 3 hours depending on the test duration that you are willing to your time that you are willing to expend on the testing. Now, the question here from the perspective of this course is we have to integrate this equation of motion. We saw that even when stiffness was completely specified, the question on how these errors grow was not very easy to answer. There were several questions on how to select the schemes of integration and so on and so forth. Now, in this pseudo dynamic testing what happens is the errors due to using finite step size and adopting certain integration schemes is compounded by errors due to experimental errors in making measurements. So, when we say that we have to apply a displacement of say 2 mm, we may not be able to apply exactly that displacement, there will be an error, and when we measure the force transferred there will be again an error due to errors in measuring through the load cells. So, all those errors also propagate. So, the major challenge in this approach is of course how to combine finite element models, part of finite element model with an experimental protocol, and also how to deal with newer sources of errors in establishing these integration schemes. Another testing procedure is real time substructuring that can conceptually be explained like this. Suppose we have a 2-story frame, we assume that part of the structure is the behavior of part of the structure is understood well and a computational model is adequate for that. The remaining part has to be experimentally tested. Suppose we make a finite element model or a simple dynamic model, this will be a 2 degree of freedom system say. Now in this analysis, this part of the structure is treated as a numerical model and this part of the structure is treated as an experimental model. N is numerical, E is experimental. So this resides on a finite element platform in our test protocol, and this is a hardware, only part of the structure is mounted on a reaction wall or a shake table. Now we again start integrating the numerical model, and while doing this we need to know what is the reaction transferred by the experimental component. So there will be an iteration. So we start integrating, we move from say 0 to delta t and find out what is the displacement. We apply this displacement, maybe a shake table in real time now, it is not pseudo time, I mean it is not static, and we measure the reaction transferred to the supports on our shake table or reaction wall, and that is transferred to the numerical model. So the integration of equation of motion and dynamic testing of the experimental component take place hand in hand in real time. So a 30-second event is analyzed in 30 seconds. That means the speed of integration and speed of testing must coincide. So this again leads to several complicating questions, and there are questions of time delays, noisy measurements, and issues like that which we need to implement while taking care of. So these hybrid testing methods are modern developments in earthquake engineering, and there actually the finite element modeling need to shake hands with experimental tools, and there are lots of newer challenges that one has to face. So this is a brief introduction about hybrid simulations as a you can take off from what we discussed in this course and probably be able to address some of these issues. So at this point we will close the discussion on this lecture as well as this course.